Okay, great. So we will talk today about another family of codes. So we saw Reed-Solomon codes last time. I will now talk about expander codes. So this is getting closer to the theme of the workshop now. We already saw some expanders being used for codes last time. Madhur's talked about the AEL construction. So this, what I'm talking about now, slightly predates it. These are the codes of Sipser and Spielman. From around 95. And yeah, so they have more claims to fame than just what I'm going to say now. But so the main aspect is that it is a route to constructing codes with positive rate and positive relative distance. So it gives codes, gives binary codes. So 0, 1 alphabet codes. With rate positive and relative distance positive. By that I mean omega 1 really. We have not seen such codes yet. We went some of the distance last time. We saw Reed-Solomon codes, which can achieve positive rate and positive distance, right? Omega 1, they satisfied R plus delta equals 1. So you can take them both to be half, for example. So, but it was in this weird setting where the alphabet size is growing with n. And in the tutorial problems, I described this procedure, or at least I asked you to describe the procedure, which takes a code like that and uses a small inner code to produce a binary code which has also positive rate and positive distance. So that operation is called concatenation. That is maybe the first way of producing codes with positive rate and positive distance as n goes to infinity. Expander codes basically provide the second explicit way to do such a thing. Yeah, so the first way was to take large alphabet codes like Reed-Solomon, Reed-Muller, and concatenate down to low to small alphabet. The second one, this works directly, and it's based not on algebra, but on graph theoretic things, in particular expander codes. So I'm going to now give a construction of these. And they also come with this extra property that they're decodable in linear time. I don't know if we will see a decoding algorithm for them, and it will be sort of obvious that it's linear time, but we'll take some, that's not the main point of this. Okay, so let's start with expander graphs. These are going to be expander graphs that are bipartite and imbalanced. So we're going to have n vertices on this side, m vertices on this side. All the vertices here are going to have degree c. All the vertices here are going to have degree c prime. Because of the nature of this, c and c prime, n and m have to satisfy some relation. C times n equals c prime times m. And okay, so we're in the setting of such a this biregular graph, and we want it to be an expander. So this G, this is my graph G. So this G is delta gamma expander if for any subset on this side, the size of its neighborhood on that side is substantially bigger than it. So I will say this better. So if for all subsets of the left-hand side, this is our left-hand side, this is the right-hand side, for all subsets of the left-hand side, which are not too big, size S at most delta n, the size of the neighborhood of S, this is what I call the neighborhood of S, is at least, well, what's the largest it could be? The largest it could be, since every vertex here has degree c, is c times the size of S. So if this is quite close to that, then I'm calling it a delta gamma expander. So it's at least C times 1 minus gamma times the size of S. This is what it means for G to be a delta gamma expander. That's the definition. Every subset, every small subset expands to almost as big as it could be. And we will set gamma to various things, but yeah, you can think of it as 0.1 for now. So delta and gamma are also both less than, yeah, they're both in 0, 1. This is the definition of a delta gamma expander. And so what we need for this construction is a construction of delta gamma expanders for certain deltas gammas, with C being constant, C prime being constant. So these are both, C and C prime are going to be constant. N and M are going to go to infinity. M is automatically some constant factor of N because of C and C prime being constant. This N is going to be the N for our codes. It's going to be the length of the code. And good. So the main input for this construction is this kind of expander. Getting this kind of expander turns out to be extremely difficult. And it took many years for such expanders to be constructed, even after Sipser and Spielmann. And right, and it's questionable whether, it's not questionable. The hard work of this construction is the construction of the expander. The expander is this extremely, it's a very useful and powerful pseudo-random object. Getting it explicitly was maybe, yeah, it was a huge achievement. And yeah, on top of that, the fact that it gives expander codes is, the fact that these codes can be defined and the distance can be proved is comparatively much easier. But then it comes also automatically with nice decoding algorithms, which we will see also. Yes?
Make a vertex expander, which is different from edge expander, obviously, we saw construction.
Oh, yes, good. So this is a vertex expander. In the bipartite case, there's no such thing as an edge expander. Right, so good. So this is a vertex expander, but it's also in the bipartite case, so it doesn't mix with the things that we saw in the last class, right? Or it does? Okay, okay. Oh, I see, yeah. Fine, but I'm insisting on subsets of the left-hand side, so it's not even full-blown vertex expander. Okay, great. So I need to say something. So first I will say that such graphs exist, and that we can get them. So first let me say what exists, and I'm not proving it, but fact, for all constants C and C prime, there exist delta gamma expanders of size n and I guess C prime, C over C prime times n. Can you see this? Where delta, or for delta, well, you can't take delta huge because you need to have enough room for the expansion to happen. You need to have enough, M should be big enough to accommodate delta n times C. So you have to go substantially lower than that. So for delta, let's say much less than C. Oh, I need M, whatever this size is, delta n times C should be less than M. Delta n times C should be less than M. So it's the same as delta n times C should be less than M. Okay, I'll say M over Cn, but it should be much less. That less is depends on gamma. So 1 over gamma square, let's say. And m I chose to be c over c prime n, so it is fine. 1 over c prime. So these graphs exist. And basically a random graph achieves this. And yeah, okay, so I'm not going to get into what kind of random model we use, but okay, so these are the graphs. And the main point is it exists for any positive gamma greater than 0 and delta being positive independent of n. Okay, so let's take these graphs. And once we take these graphs, I'm going to define a code coming from it. So this is the code coming from G. The code words are going to be functions on the left. So the code itself is functions from the left-hand side to 0, 1, such that, yes, I'll do it again here. We will have zeros and ones written on this side. Each vertex on this side is going to be adjacent to some number of these, and we're going to insist that their parity is 0. For every right vertex, consider its neighborhood, we insist that the parity of that is 0. That's that for all v in the right-hand side, the parity of f of u adjacent to v is 0. This collection of functions, which is basically element strings in 0, 1 to the n, this collection of functions is going to be the code. Okay, so first, so is the construction clear? It specifies a set of 0, 1 strings by some constraints. It's not clear yet that there is even one string satisfying this, but it will be. And it has to, so we have to show that there are many code words in this so that we get positive rate. We have to show that any two strings here differ in many coordinates so that we get positive distance. Okay, so first let's see positive rate. C is a linear code, is that clear? It's a linear code over F2. The 0, 1 is now F2. The parity is basically sum mod 2. It's a linear code because they're defined by linear constraints. What is the dimension of the code? I see. So it's actually, in fact, the way, at least based on the text, it's not clear that C has any code words, and it may not, other than 0. But from my picture, you should have seen that M was smaller than N. Was it clear that M was smaller than N? It was clear that M was smaller than N. Okay, good. So when M is smaller than N, there are going to be many code words. So C is a linear code over F2. So it has a dimension, and we can talk about the dimension of C. What can we say about the dimension of C? N minus M. We applied M constraints. The dimension of this is at least N minus N. It's originally, I mean, all strings is N dimensional, and then we applied M linear constraints. So the dimension is at least N minus N. And the way I set things up, this is N times 1 minus C over C prime. C over C prime. Okay, so if you set it up with C less than C prime, both being constants, and C is less than C prime, then this is some positive number. It's a positive constant independent of N. So the dimension of this is omega N. So rate, which is equal to dimension of C over N, is 1 minus C over C prime, and this is omega 1. Because we will fix it with C being constant, C prime being a larger constant, and that's it. So that's why this has good rate. I also need to show that this has distance. And this is where we'll use the expansion. So distance, so yeah, so this is more tricky. First, I want to say that, so this is a linear space. So this fact, I didn't exactly say it last time, but yeah, when you have, suppose you had two strings F and G on the left-hand side, which are both code words, then F plus G is also a code word. And F plus G is one precisely where F and G differ. So actually I should have said F minus G, which is the same thing in this case. F minus G is one precisely where these code words differ. And since it's a linear code, F minus G is also a code word. So it suffices for the distance to show that any non-zero code word has at least so many ones. Okay, so the claim for this is that any non-zero F has in the code has at least delta n ones. This will mean that the code has distance delta. And C has relative distance delta. Okay, so I'm going to now show this. Can you have a string, you have an assignment of zeros and ones on this side with very few ones? We want to show that this is not possible. There are ones, but there are very few of them. Can you have an assignment of zeros and ones here such that all the neighbors on this side have an even number of ones in their neighborhood? This is exactly the question of is there a string in the code with a small number of ones? Okay, and this is the expansion is going to sort this out for us, but it's not just any expansion, it has to be really good expansion. And suppose F from the left-hand side to 0, 1. So we now know this 0, 1 is F2, so I keep it F2. Is non-zero on the set S. So this is the set S, and these are where the ones are, and everywhere else it's 0. These are 0. Can you have such a set having all the constraints satisfied? A small set S of size only delta n, such that all the vertices on the right have, when you take parity of the neighborhood, it should be that, well, the zeros contribute nothing to the parity, only the ones contribute. It should have an even number of neighbors in S. Okay, and this is not possible. So here is, so we want to show that there exists a vertex V on the right such that V has an odd number of neighbors in S. Do we agree at this point that if we show this, we have an assumption, right? And size S is at most delta n. Do we agree that if we show that for whenever you have a set of size at most delta n, there is a vertex V on the right which has an odd number of neighbors in S, then this code has distance at least delta n. You can ask me questions now. I haven't gotten a question all day, so right? I haven't had the question yet, so. We will need to assume something about gamma. So we will need gamma to be at most half for this to succeed in showing this. And I guess that you actually need that. I'm not 100% sure about this. Okay. Okay, so and now the claim is if gamma is less than half, so I'm starting from just basic expansion, but I want to somehow get an odd neighbor, a vertex with an odd number of neighbors in S. So if gamma is less than a half, in fact, there is a vertex V in R such that V has one neighbor in S. Yeah. Right. What's the general principle that underlies this? Good question. Sets which have an in a big expander, meaning if it has high expansion, small sets have unique neighbors. That's the principle. If you're a big expander, small sets. Big expander, by that I mean gamma is small. Then small sets will have a unique neighbor. So this is a general fact about expanders. Yeah. Yeah.
There it's just like local distance gives local.
Right.
So almost always that. Yeah, vertex expanders I kind of understand less, but yeah, here.
Right. So there's another construction. These are called the Tanner codes. We'll see that later. Where there it's much more. It's closer to the principle that expanders are samplers, and it's the kind of principle we saw last time in Mother's talk. Right. And then you can take a small object which has distance and amplify that. It's some local to global phenomenon. Okay. So why is this? This is because of extreme expansion. If a set has so many neighbors, then these neighbors can't all be coming from these neighbors can't all have two neighbors within S. We have a set S, and I'm going to look at the neighborhood of S. Oh, S is relatively small, and it expanded so much. I mean, if all the vertices here had at least two neighbors, then so we know that there are C times size S edges between them. But if every vertex here in the neighborhood, so you know it has positive number of neighbors in S, and if none of them had an odd number of neighbors, if none of them had one neighbor, then all of them have at least two neighbors. So this should be accounted for by size of gamma S times 2 so if every vertex in gamma S had two neighbors, at least two neighbors in S, that's the knot of there is a vertex with one neighbor. If every vertex in the neighborhood has at least two neighbors, then this will happen. And this means the size of the neighborhood of S is at most C over 2 times size S. And this violates expansion if gamma is less than half. In fact, more is true, and we will need it soon. The number of unique neighbors of S. What is a unique neighbor of S? It is a neighbor of S which has exactly one neighbor in S. I'm using neighbor in both directions. The number of unique neighbors is at least 1 minus 2 gamma times C times size S. And yeah, I'll call this a fact so that I don't prove it. And it is exactly this proof. It's about budgeting, how many edges. Yeah. In the neighborhood, there are some unique neighbors and there's some non-unique neighbors. The non-unique neighbors have at least 2 neighbors into S. So when gamma is half, when gamma is less than half, we're very happy. We get at least 1. And later we'll also need the fact that there are many unique neighbors. So for the decoding algorithm. But at this point, we are here. And now once we put all this together, we get that if S has, yeah, so we get what we wanted, right? So sets of size at most delta n always have at least 1 unique neighbor. So we get that distance, the code C has minimum distance at least delta n. And in fact, it has distance slightly more than delta n. It goes all the way up to 2 times 1 minus gamma times delta n. There's some small variation of this argument, an improvement of this argument that gives us, but we're already happy at this stage. Questions about this? So we got positive rate and positive distance. We didn't do that much work. Right? So all the hard work happened in the construction of the expanders. The construction of expanders is, I mean, it's non-trivial. It was, I will give some references for this. And of late, there's been a flurry of activity around this problem. So the original construction was by CRVW. This is the Kapalbo, Reingold, Vadhan, Wigderson, using a variant of the zigzag product. And this was the explicit construction. Of such extreme expanders. And then more recently, Golovich and Amnon and so Amnon Tashma, Cohen and someone. Amnon? He doesn't remember either. Okay, and someone. I think Amnon student have a new approach. I mean, have a much cleaner approach. The CRVW is quite involved. A much cleaner approach to producing these things, and these use HDXs based construction. In a very elegant and clean way. So they use HDXs, which are spectral things, to construct this kind of combinatorial expansion. This kind of combinatorial expansion is not implied by anything spectral. Where by anything spectral about expanders, but apparently, after you read these papers, using HDXs, one can using the spectral properties of HDX expanders, which we don't even know what they are at this point in the week. You can come back in. Yeah. Roth. Oh, great. Okay. And Roth. Oh, yes, yes. So there are even, and now there are some even more papers, yes, by Paradis and Zhang and Lubotsky et al. So there are more, very, very recent. There's a lot of activity around construction of expanders using HDXs. Yeah, very recent stuff, which construct expanders that expand in both directions, and vertex expanders, and a bunch of things. Okay. So now we'll see how to decode these codes. So we saw an explicit construction of codes modulo this huge input, but now we'll see how to decode them, and this will be quite clever. So what's the decoding problem? I give you a string written on the left-hand side, which is promised to be close to a true code word. You have a string on the left-hand side, which is promised to be close to a true code word. And we want to find the true code word near it. So we have some corrupted F. And for my picture, I'm going to take so there's a true code word, and we're going to corrupt it in a few locations. Okay, and I'm going to call that set S again, because all subsets of the left-hand side are S. And we have a promise that S is small. This is the key part. So that's why we can talk about this particular set S. So we've taken true code word, we've corrupted a small number of coordinates, and good. And we can look at all these constraints and see what is the value of the sum at those constraints. Okay, so if it was a true code word, we know that the value of the sum over here, all these sums would have value 0. Right? That's the definition of true code word. But now you go to a few of these bits and you flip them. Then on this side, since it's not a true code word, they're not all going to be 0. Several of them will be non-zero. Good. So we want to somehow use the fact that, we want to use the promise that only a few of these bits have been flipped to help identify which bits to unflip. Okay. And so the idea is to consider the set of constraints that have been violated and inspect them and see if we get any clues. So a good motivation for this is, I suppose you go and flip only one bit. So we have a true code word previously written. At that point, all the constraints are 0. Now I go to one of these bits and I flip it from 0 to 1. Which of these constraints are satisfied and which ones are not? Which of the constraints sum up to 0 and which of them sum to non-zero? Right. Any constraint that involves that vertex is violated. So that constraint sums up to 1, right? Because previously it summed to 0 and the flip of it changes its value. So at this point it's easy to spot which vertex on the left is the one to flip. It is the vertex whose neighborhood equals the set of violated constraints. If there were 2 of them which were flipped, well, you have a promise that's going to be the union of 2 neighborhoods. If you go inspect each of the vertices on the left and see how many of their neighbors are violated constraints, you'll get a hint as to which of the vertices on the left needs to be flipped. Okay, so the algorithm is very simple. Like we already had these short description algorithms. So I'll give you a short phrase to describe this algorithm. But after I tell you, you won't discover the algorithm. Rather, maybe you'll discover the algorithm, but you won't discover its analysis. Well, not so easily. Okay. So the algorithm is belief propagation. And this is, it's a statistical physics, machine learning kind of word, propagation. propagation. All these constraints, they're either happy or unhappy. We are trying to make these constraints all happy. So we're looking for operations that we can do on this side to improve the number of happy vertices, happy constraints. So let's look for vertices on the left such that flipping them will improve the number of happy constraints. So each constraint is either happy or not. It's, by happy I mean it's happy with the state of affairs of its neighbors. Is their parity 0 or not? We look for a vertex I guess U on the left, such that it has more unhappy neighbors than happy neighbors. And flip it. That's the algorithm. Keep doing this. And the claim is, so this needs actually a bit more gamma. Gamma needs to be even smaller, maybe 1/4. And at that point, the claim is if the fraction of errors is, if the original fraction of errors is smaller than half the minimum distance, then we will end up with a true code word at the end of this. There is a clear progress measure. What's the progress measure? Number of happy constraints or unhappy constraints. Number of unhappy constraints keeps reducing because we are only going to look for such a vertex. That there is such a vertex is not clear, but right, and that there will always be such a vertex. So as you keep going. Okay, so let's see that. So this is the algorithm actually. Yeah, so claims. So this is, I guess, the main fact, right? Theorems. That if our given received word has distance less than delta over 2n. Actually, you can. It's slightly better than that. That's because, and that's not inconsistent because actually the distance of this code is more than delta n. So I will prove it for something slightly larger than this. This has less than distance less than delta over 2n from the code. Then this algorithm. Oh, no, I also need if this and also gamma is less than 1/4, then this algorithm finds the nearby code word. That's what the claim. This decoding algorithm looks nothing like the Reed-Solomon decoder, right? The Berkeley-Campbell's decoder was some black magic coming out of nowhere. It found the entire solution in one shot. Here there was some notion of progress and iteratively improving and going. It looks more like an optimization algorithm. Right. Okay, so why is there a vertex which has more unhappy neighbors than happy neighbors? We have a set S. These are all its neighbors. Okay. Yeah. So this neighbors is a different neighbor, right? So I want to look for a vertex here which has more. I want to look for a vertex here. Yeah, sorry, that has more unhappy neighbors than happy neighbors. What are unhappy neighbors in terms of the set S? This S is the set of corrupted locations. What are the unhappy neighbors? Those are they are the vertices which have an odd number of neighbors in S. We cannot argue about odd. We can only argue about unique. So let's even think about that. These are vertices. The unhappy neighbors of, or the unhappy constraints are those which have an odd number of neighbors in S. I want to say that there are many. I cannot argue about odd, so I'll argue about unique. I want to say that there are many unique neighbors of S. There are. That was our fact. There are 1 minus 2 gamma. There are many vertices here that are unique neighbors of something in S. So I'm going to say this now. So we know that there are at least 1 minus 2 gamma C size S unique neighbors of S. So okay, I should zoom in on the picture. This is S. This is its full neighborhood. And this is the unique neighborhood. And this is the rest. And the unique neighborhood is huge because I've assumed gamma is small enough. Gamma is less than 1/4. So in fact, 1 minus half times CS, this is more than half of the neighborhood of S. So this is at least half CS, which is at least half, yeah, okay. If the unique neighborhood is at least half CS, each vertex here has some number of unique neighbors of its own. There must be at least one vertex here which has at least half C unique neighbors. Right? The total number of unique neighbors are always assigned to particular vertices here. All the unique neighbors come from, each unique neighbor here is unique to one of these guys. So there are totally half CS unique neighbors. Each of them came from different elements out of these S. So the average number of unique neighbors per vertex is at least half C. So this implies there is some U in S which has at least half C unique neighbors. I'm not done. That's why. This would have worked even with delta. Right? I didn't use anything. I used the fact that S is of size at most delta, and therefore there is expansion. So I keep doing this. So I found that there is a unique neighbor. Good. So I can keep doing this. I found that there is. Oh, sorry. What did I find? I found that there's a vertex here which has more than half of its neighbors being unique. All the unique neighbors are unhappy. So it has more than half of its neighbors being unhappy. So it is a vertex which I can use for this step. So I flip it and continue. And I keep doing. So I'm done. So why do I need that? A vertex outside S will have true. A vertex, right? So there's no promise that What I just showed is that there is such a vertex, so I can do this. But okay, but the number of unhappy constraints reduced, and I keep reducing the number of unhappy constraints. So I'm not promising that I flip a vertex in S. I'm just promising that the number of unhappy constraints reduced. Keep doing this, it will end up being 0. So this part is okay. So why am I not done? You might go to another code word. Right, but what's preventing? Oh, I see. Right, that's fine. The problem is not find a code word. The problem is find the nearby code word. Yes, you might end up at another code word. That's true, but there's maybe a problem even before that. So someone was saying something. Right. If this process stopped within delta over 2n steps, then you know for sure you hit the right code word, right? Because in delta over 2n steps, yes, that's true. So that is a sufficient condition for knowing you're right. Yeah, but there's a problem even before this issue of reaching a different code word, which is that, so as you do this flipping, you're no longer in this promise setting where the number of errors is less than delta n. So this proof that there exists such a vertex u doesn't work anymore. This proof worked only for the very first step, where I knew that there were exactly, or where there were at most delta n corruptions on the left. But as the algorithm proceeds, it will go into uncharted territory. We will be on the left hand side, we will have an f which is no longer promised to be so close. So right, so this is where I need this delta over 2n assumption. I need, or at least something better than this. I should not have been able to decode I should only be able to decode from half the minimum distance. I shouldn't be able to decode it from beyond in general. Okay, so yeah, so that is the issue. So we need to maintain the property that that S is always that the set of corrupted left-hand vertices is small. So what we really should have shown was, suppose you had a small number of corrupted vertices on the left, then you can always, actually we did show that. So let's sort this out properly. Right, so number of unhappy constraints starts at something, okay, we'll talk about that, and strictly reduces. On the other hand, is the distance of our current word from F, the true code word. That does not monotonically decrease. I'm not promising that. But this always is at most something, which is so at most delta n. We need to maintain, so we need this property in order to get in order to always have a vertex to flip. So what we have shown is that if this property holds, then we have a vertex to flip. I want to make sure this property always holds. How do I make sure this property always holds? I'll make sure, so there is a two-way connection between the number of corrupted coordinates and the number of unhappy constraints. we will use the fact that the number of unhappy constraints is small. This we know at every stage of the algorithm. It started off at something and it will only strictly reduce. So number of unhappy constraints is small. This will imply that the distance of the current word from the true code word is moderately small, and we'll make that moderate delta n, and then this will finish out. So what does the number of unhappy constraints start off at? It starts off at original distance, delta of received word and true code word, times C times at most. Right? Because only neighbors of S can initially be unhappy. And the number of neighbors at most C times size S. So it starts off at that. And this means, good, so at every stage of the algorithm, we know that the number of so at every stage of the algorithm, the number of unhappy constraints is at most C times delta n over 2. This means the size of, the distance of our current word from the true code word only changes by 1 at a time, right? Because we're only flipping 1 bit at a time. So we're moving around in space. Right? This is 0, 1 to the n. We start, this is a true code word. We start off somewhere and we move around. I want to say we never go too far. That's what I want to say. If we go too far, then I lose this property. The moment the distance goes more than delta n, I'm not able to prove this, the existence of the bit to flip. So we move around. If we ever end up far, then consider the step where we went far. So consider S at the time, at the step where the size of S became delta n. At that step, how many unhappy constraints are there? There are lots of unhappy constraints. More than this. So we could not have been in such a state. So if you ever manage to go far, the number of unhappy constraints is guaranteed. So if you go too far, there's no promises anymore. Only if you go on your way to very far, you crossed delta n. At that stage, you can apply the expansion hypothesis. Right? You can't say anything about expansion when you're already 2 delta n far. There's no expansion says nothing there. But if you're delta n far, you're on your way to 2 delta n far, since we were moving only 1 step at a time, you will have this violation. So then number of unhappy constraints is at least by the unique neighbor expansion. All the unique neighbors of S are unhappy, so it's at least 1 minus 2 gamma delta n, which is at least delta over 2n. No? C. Okay, I'm not so happy with this. I don't like photo finishes. This is too close. Oh, I see. So if gamma is more than 1/4, yeah, fine, then this is more. But okay, we could have made gamma 1/8 or something, and then it would be true. A comfortable win. Yes, okay. So what's the moral? We found that you never go too far. You never go too far because you never can go moderately far. Because we started with the number, initially it's at C delta 1 over 2, and it only reduces. Initially, the number of is C times at most C delta n over 2. Yeah, that's the promise. No, I mean, the promise is that's at most delta n over 2 far. Therefore, the number of unhappy constraints is at most C delta n over 2. And then it keeps reducing. So we're always like this. Right. Yeah, so there's the subtlety about, you can't say that far away words have many unhappy constraints. Can you say that far away words have many unhappy constraints? Oh, yes. Let's say, you cannot say that strings that are far away from the code have many unhappy constraints. No, far away from the code, not the code word. Then it's okay. If you have a string that's far away from the code, do we know that it has many unhappy constraints? This is exactly the question of local testing. This is exactly about locally testable codes. If you have a whole bunch of constraints, each of them just involving C prime many coordinates, and they have the property that whenever you have a string that's far away from the code, many of the constraints are violated. Then you have a locally testable code. We haven't defined locally testable codes, but I mean, HDX encodes is a thing just because, I wouldn't say just because, but largely because locally testable codes exist. So yeah, so this is the main phenomenon. That is not, yeah, that's not true for any expander code. In fact, okay, so I want to ask a question, but okay, so but let's resolve this first. So so initially the number of unhappy constraints is something, it only strictly reduces. Because it keeps strictly reducing, one way to show that we never go too far is to show that if you ever went far, on the way, you must have had a large number of unhappy constraints, more than this. Okay, now here is the question. Start with show me that there are strings that are far from the code but do not violate a lot of constraints. Not any expander graph because locally testable codes exist. Though, yeah, I mean, those are for a super duper special. I mean, if you view it in this language, it is for a very special expander which has a lot of extra properties. Yeah, a lot of extra properties that you do not expect at all. So, yeah, for a random expander. So let's say there's nothing special about your expander. You can take a code word and completely complement it. Okay, is that not a code word? I mean, it's far away from one code word, that I agree. It's very far away from one code word, but is it not? I don't know that it's not in the code. In fact, if the all one string is in the code, which let's say if C prime is even, I guess that's a code word. So counting, yeah, not clear. Okay. Okay, so let me show this to you. So this is the main idea of Ben Sasson, Harsha, Ratchnadikova. Well, one of the main ideas there, which shows that expander codes are not locally testable in general. Take an expander code like this. I took this expander code. Take one of these constraints. Oh, okay. Right. Okay, so this is the secret stuff here. So take one of these constraints and remove it from the code. Would you agree that this is an expander code too? I took an expander code. This is in my expander code. I took one of these constraints. I took this vertex and deleted it. This is still an expander code. Right? I mean, okay, we lost regularity, but regularity was never the point. Sets on the left still have lots of large unique neighbor expanded, large number of unique neighbors. Exactly the same thing holds. So if you remove this vertex, now it's a code of dimension 1 larger. Well, it should be 1 larger. If these constraints were chosen redundantly, then maybe it won't be, and that's exactly why there is scope for having locally testable codes. But if you took generic expander graphs, then all these constraints will be linearly independent. Removing one will reduce the dimension, will reduce the number of constraints by 1, thus increasing the dimension. So now we have another code which has dimension 1 more than our original code, containing our original code, and it satisfies all constraints. The code words of that satisfy all constraints except this. So now take a code word that is part of the new code but not part of the old code. That string will satisfy all these constraints except this. And it's far away from all strings of the old code because the new thing is also an expander code. So any 2 strings are far apart from each other. So this is the reason. This is from BHR. This is the reason that generic expander codes are not locally testable. It's precisely this phenomenon that the number of constraints does not measure, the number of violated constraints does not measure the distance to the code. You need some redundancy here to foil this argument. And yeah, and so finally so I do not know actually how the final LTCs look. Pavel will probably tell us. Yeah, I mean, from the point of view of this, yeah, I mean, there is a lot of redundancy. In fact, every constraint that if you drop it, there are other constraints that make up for it. This has to be the case, otherwise this kind of proof. Yeah. Yes, good. So so the rest of BHR, so there's a lot more in BHR. It shows that if you take a random expander code, there are probably no others. There are probably no other tests of this low arity, and any test of low arity is a union of is simply the sum of a few of these constraints. So if you want a constraint of arity 2C prime, you take the sum of 2 of them, and 3C prime, it takes the sum of 3 of them, and those are the only ones. So ultimately, one is showing that the only low weight constraints on the code words of this code are what come from, which are what is obvious from the expander code definition. And so once you show all that, then it's, yeah. Oh, we can take gamma all the way to 0. I mean, any constant bigger than 0 is okay for, I mean, such expanders exist. Is that the question? Oh, gamma, you mean capital gamma? Oh, yes. If you keep removing vertices, oh, you mean little gamma? Oh, I see. How many vertices can you remove while still maintaining the property of being an expander code? I'm not sure. At least for this argument, we just needed to remove 1 and then we were happy. But yeah, I'm not sure. But the expansion automatically gives some robustness. I guess once you take out the full neighborhood of 1 vertex, maybe then you're in trouble. I don't know if you're in trouble then. Yeah, then maybe you violate expansion for some trivial reason. Yeah, so you have to be careful how you remove. But for removing 1, we were certainly okay. Okay. How am I on time? 6 minutes past. Okay, good. So in the remaining, okay, great. So next lecture, Mrinal will continue with algebraic codes, and we'll come back to expanders in tomorrow.